Some people make a lasting mark on the world, and we thank them by honoring their achievements. Every year, we honor 6 groups of people with the Nobel Prize. There's Nobel Prizes for physics, chemistry, medicine, literature, economics, and even peace. But I guess no one told Alfred Nobel that fields like mathematics or computer science also exist. But that's alright. People in these fields started their own awards and just asked that everyone think of it like a Nobel Prize. The Fields Medal is considered to be the Nobel Prize in mathematics, and the Turing Award is the Nobel Prize of computer science. That's cool and all, but you clicked on this video because you wanted to learn about the Nobel Prize of statistics. I could be a little biased here, but I think that statistics is just as important as math or computer science. All areas of science produce their own types of data, so at some point, everyone is going to need statistics in some form or another. So, is there a Nobel Prize of statistics or not? And if there is, what does it take to win it? And today you're going to learn the answers to both of these questions. If you're new here, welcome to the channel. My name's Christian and I'm a PhD candidate in biostatistics. You're watching Very Normal, a channel for making you better at statistics. Maybe not as good as the people in this video, but still better than your friends. Let's see what this award is all about. The Nobel Prize of Statistics is called the International Prize in Statistics. They couldn't think of a famous person to name the prize after, so they just gave it a complicated name, which, if you think about it, is pretty on par for the course for statisticians. Don't feel bad if you've never heard of it before. The prize only just started in 2016, and it's only awarded every other year, so at the time I'm editing this video, only 4 people have received it. People who win the Nobel Prize win about $1 million, a 24-karat green gold medal, and a diploma. Winners of the Field Medal also get $15,000, whereas winners of the Turing Award also get a few $100,000. So what do the winners of the International Prize in Statistics get? A cool $80,000, and what appears to be a nice piece of paper. To be considered for the prize, your peers have to submit a nomination packet in your name. The prize can be awarded to teams or organizations, but so far has gone to individual people. These people are recognized for a single work or a body of work that has significantly shaped the field of statistics. And finally, the winner needs to be alive at the time of selection. All nominations are considered by a selection committee formed by the 5 biggest statistical associations in the world, and a winner is selected near the end of the year. So that's the award, but what exactly does it take to win it? To answer that, let's look at the past winners and delve into the work that earned them a Nobel Prize equivalent. The inaugural prize was given to Sir David Cox in 2016 for his groundbreaking paper on the proportional hazards model. Sir David Cox was a professor of statistics at several universities, including the Imperial College of London and Oxford University. And I'm not calling him Sir to be polite, he was actually knighted in 1985. Unfortunately, he passed away in January of 2022, but he leaves behind a vast legacy that statistics students still learn from today. In 1972, Sir David Cox published this paper in the Journal of the Royal Statistical Society Series B, titled Regression Models and Life Tables. The paper deals with the problem of failure times, also known as survival or time-to-event data. Time-to-event data looks at the time it takes for some pre-specified event to happen, and it's distinct from a regular continuous outcome. For example, this time could be how long it takes for your new laptop to break, or the time it takes for you to find a parking space at the mall. It also includes the ultimate outcome for us all, our own mortality. Cox's paper was significant because it gave us a tool to examine the effect of a variable on the time to an event, whether or not it will shorten or extend this time. It doesn't take a statistician to recognize that this type of model is a really important tool to have. Cox's model is a regression, meaning it models the relationship between some independent variable x and some time to event variable t using a well-defined formula. It has 2 components to it. The first is a function of time, commonly denoted as lambda t. The second component is an exponential function that contains both x and the parameter. This type of model is also known as semi-parametric because it contains both a non-parametric and a parametric component. The part we're actually interested in is this parameter, and I'll explain why in a bit. This lambda t is called the hazard function, and it's one of the ways that we can describe the time to an event. There's no time to get into the gritty details of survival analysis, so you'll just get the bare essentials here. This expression is the formal definition of the hazard function. I know it looks a little crazy, but I'll walk you through each of the bits. The numerator here is expressed as a conditional probability. We could interpret it as follows. Given that a part of the population hasn't experienced the event yet, this is the probability that they'll experience it in the following window of time, which is this delta t. This delta t is also here in the denominator, and this limit here indicates that this window of time should approach 0. If it's been a while since your last calculus class, you would interpret this whole expression as a rate. The hazard function describes the so-called instantaneous rate at which the event is happening at time t. I know that's a lot, so it's worth looking at a specific hazard function so that we could work out the logic of what it's supposed to represent. Let's say that the event we're studying is death in some population. This means that t represents the time until someone passes away. A plausible hazard function for this event could look like this. Let's see what happens as a person gets older in this population. When we're born, we're really fragile. There could be a lot of things that are fatal to newborns, so we would expect more mortality at the start of this population's life. But after some point, we're good. With healthy, robust bodies, the rate of death is really low in the population at this time, so the hazard function is barely above 0 here. But of course, that doesn't last forever. At an advanced enough age, there are more and more things that can harm us. As our health and bodies get more fragile, we also expect the rate of death to increase as older people get older. The shape is so common that it has a name, the bathtub curve. But you can also have hazard functions that are purely increasing or decreasing, which can happen with different types of events. Looking back at the Cox model, this lambda t represents the hazard function for the reference group who have an x value of 0. For example, this could be a placebo group in a clinical trial. The only way that this hazard function can be changed is through this term here. If someone is on active treatment, then x takes a value of 1, and we'll get the product of the original hazard function multiplied by this constant here. Depending on the value of the parameter, it can change the shape of the hazard function in different ways. For simplicity, we'll say that the baseline hazard function is increasing. If the treatment is beneficial, the parameter will be less than 1, and this will stretch the hazard function, causing it to rise more slowly. It would take a longer time for someone on a treatment to reach the same hazard as someone in the placebo group. Conversely, if the treatment is actually harmful, the hazard function will contract, leading the hazard to rise faster for the treatment group. The structure of Cox's model assumes that the hazard functions for the two groups can be written in this proportional form, and that's where the model gets its name, the proportional hazards model. I described how this model might work for a single binary variable, but the same logic could extend to continuous variables or multiple predictors. Cox's paper is so important that it appears on Nature's list of the top 100 most cited papers of all time, and it's allowed us to identify factors that shorten or extend our life here on Earth. The second prize was awarded to Bradley Efron in 2018 for his work on the bootstrap. He's currently Professor Emeritus in Statistics and Biostatistics at Stanford University. One of my first breakthrough videos was on the bootstrap, so his method will always have a special place on this channel. The bootstrap was first published in 1977 in a manuscript titled Bootstrap Methods, Another Look at the Jackknife, and this paper gave rise to a simple but deceptively powerful idea. When we're interested in studying a population, we collect data on them. For example, you might want to know how long they typically live, or what proportion of them have a chronic disease. From the data, we create an educated guess, or an estimate, of the population characteristic we want to study. Often, we only collect one dataset, but statisticians know that a slightly different dataset will create a slightly different estimate. It's not enough just to get that single estimate, it's important that we can characterize how this estimate might change with different datasets. In other words, we also need to understand the uncertainty or variance in our estimate. To understand this uncertainty, we need to know the probability distribution of this estimate, which usually means we need to collect different datasets. But collecting data can be very time-consuming or expensive. So most of the time, we only have one dataset, and that's it. You can't study uncertainty with just one dataset, so we have to turn to statistical theory. For example, we often rely on the central limit theorem to give us the probability distribution of our estimate. One problem with theorems is that they often come with assumptions and requirements. So if these can't be met, then we can't safely use the distribution guaranteed by the theorem. This is where the bootstrap comes in. Instead of trying to gather different independent datasets, Efron's idea was to create new datasets from the original data itself. This is where the bootstrap gets its name. We create so-called bootstrap datasets by sampling from the original data with replacement. This means that it's possible to have duplicate observations in the same bootstrap data, but that's not really a problem. From the point of view of the bootstrap, if one observation came from the population, it's not impossible to observe a second observation that's close to or even the same value as the one we just got. And this can extend to multiple observations as well. From each bootstrap dataset, we can calculate a bootstrap estimate. This results in a collection of estimates that are all slightly different since they use different data. We can then use this collection of estimates as a stand-in for the true probability distribution of the estimator, and by extension, use it to characterize its uncertainty. You can calculate other useful values like a bootstrap p-value or a bootstrap confidence interval, and use these to conduct valid hypothesis tests. And the bootstrap can even work for more complicated estimators like functions. You can see an example of this in Netflix's technical blog, where they use an advanced version of the bootstrap to characterize the uncertainty in the quantile function. The bootstrap is useful not only because of what it can do, but with how accessible it is to non-statisticians. Statisticians come up with fancy models all the time, but they're only really useful if the statistician is there to teach other people how to use it, or the method is simple enough for a general audience to use. With the proliferation of powerful computers and laptops, the bootstrap is now in everyone's hands. Before I get into the next winner, let me ask you a question. Without looking it up, can you name at least one famous woman in statistics? I'll give you a few seconds. If you didn't know, that's too bad, but after this video, you should have an answer. The third prize was awarded to Nan Laird in 2021 for her work on the random effects model. She's currently a professor emerita in biostatistics at Harvard University. Nan Laird's seminal paper on the random effects model was published in Biometrics in December 1982. It was framed to tackle the problem of longitudinal data that's observed repeatedly over time. But as I'll explain later, the problem of longitudinal data is a problem that's much more common than you might expect. Let's say that we're studying the effect of pollution on a child's lung function. It's thought that this effect will change over time, so we'll also need to gather data from these children as they grow up. The end result is multiple observations per child in your data. This is a problem. Since we're looking at the relationship between pollution and lung function, the problem calls for a regression. But a linear regression assumes that the errors in your data are independent and identically distributed, the well-known IID assumption. But if two observations come from the same person, do you think that it's plausible that their errors are independent of each other? No. Data from the same person is very likely to be correlated. So, longitudinal data inherently violates the IID assumption. Therefore, linear regression is not a good solution here. Cue the random effects model. It has a form similar to a standard linear regression, but has some additions that make it much more interesting. The random effects model is what's known as a two-stage model, or a hierarchical model. To make sense of it, we have to understand what these two stages represent. In a standard linear regression, all the children are modeled to have the same treatment effect, represented by this parameter here. Think of this as a population-level effect, the change in lung function that this population of children will experience thanks to pollution. The random effects model goes a step further. Not only do the children experience an overall change as a group, they're also allowed to vary slightly from this fixed change. In the model, you can represent this using a sum, the fixed effect plus some subject-specific deviation, which in total equals the child-specific effect. It's not just for the treatment effect either. The children could also be modeled to differ in their baseline lung function as well. These deviations are also known as random effects, and they give the model its name. The model states that there's an average effect that all the children will experience, but each child will have a specific effect that deviates slightly from this average. These deviations themselves are assumed to have a normal distribution with its own variance. While we don't directly see what each child's specific deviation is, we do observe repeated outcomes for each of them. The treatment effects form the first level of the hierarchy, while the distribution of each child's data forms the second level. Without getting into the technical details, by specifying that there's a distribution on the child's specific effects, the model can actually help account for correlation that comes from repeated measurements. Like I mentioned earlier, Nan Laird's method was originally framed for longitudinal data. With this type of data, observations are correlated because they come from the same person. Think of an individual person here as a cluster. Depending on our context, what defines a cluster can also change. Clusters could be people, locations, or even something abstract like an individual research study. This is the idea behind the meta-analysis, widely considered to be the highest form of scientific evidence, even beyond that of the hallowed randomized controlled trial. The fourth prize was given to Kalyampudi Radhakrishna Rao, also known as C.R. Rao, in 2023. Unfortunately, C.R. Rao passed away on August 2023, but thankfully he was still able to accept the reward before his passing. Before his retirement in 1991, C.R. Rao was a professor at the University of Buffalo and Penn State. Sir David Cox, Bradley Efron, and Nan Laird each contributed a model or a method that researchers of all kinds can use. For some people, this can feel more concrete, since a model is something you can use with just a few lines of code. In contrast, the works that C.R. Rao are honored for are more on the theoretical side. Most people are probably not aware that they're benefiting from the implications of C.R. Rao's work, but I'm going to try to change that today. For brevity, I'm only going to talk about one specific work in this video, the Khmer Rao lower bound. When I was explaining the motivation behind Bradley Efron's work, I talked about how we take data and construct educated guesses about specific aspects of a population. The bootstrap answers the question of uncertainty behind this estimate, but there's an even deeper question behind all of this. How do you even make an educated guess in the first place? Remember that the only thing we actually see is data, just a bunch of numbers. With just the data alone, for students learning statistics, this point is often glossed over. They're told a formula to use for stuff like the sample mean and the sample variance, but they don't stop to question why we use them in the first place. As you might guess, C.R. Rao's first work lies at the very heart of this question. We know that data is inherently random, so the estimates we derive from them are also random. Because of this, we need to characterize the variance in our guess. As it turns out, one way to judge how good an estimate is its variance. We would much prefer to have our guesses have small variance so that they stay clustered together. Even if the estimates vary around the true unknown quality that we want to know about, smaller variance helps us hone in on what it could be. Conversely, if an estimate has high variance, we might get wildly different or even conflicting guesses about our quantity of interest. The key idea here is that lower variance is better. In 1945, C.R. Rao published a short article titled Information and the Accuracy Attainable in Estimation of Statistical Parameters. This paper establishes that there's an absolute lower bound on the variance that any guess can have. This is the famous Khmer Rao lower bound, discovered independently by C.R. Rao and a Swedish statistician, Harald Khmer. This value here is called the Fisher information, which I definitely don't have time to cover here. Just know that no matter what your method is for creating estimators, the variance can't be better, i.e. lower, than the Khmer Rao lower bound. Some of you might ask, okay, there's a lower bound on the variance for any estimator. So what? The implication of Khmer and Rao's work is that if you do have a way to create an educated guess and its variance equals the lower bound, then, in a sense, you have a good guess. And not just good, but an optimal guess. Do we have ways to make these so-called optimal guesses? And the answer is yes. It's maximum likelihood estimation. Any model that uses maximum likelihood estimation achieves the Khmer Rao lower bound. Anytime you run a linear or logistic regression, you're using maximum likelihood. Cox's proportional hazards model, maximum likelihood. The random effects model, maximum likelihood. You might not know it because R hides this process in the background. You get to benefit from the properties of maximum likelihood while avoiding the process of having to calculate the guess in the first place. Textbooks and classes often stop at the minimum variance result of maximum likelihood and don't explain why it's important. If our estimator has the smallest possible variance, it also means that we get the smallest possible confidence intervals, even before considering other factors like experimental design or sample size. In October this year, the nominations for the 2025 prize will start. Since I run a statistics channel, I thought it would be fun to make my own prediction. This channel is so far mostly focused on statistical inference. We can't forget that the problem of prediction is also a statistical problem, even though it's been given many names. Statistical learning, machine learning, data science, artificial intelligence, all of these deal with prediction. Given that generative AI like ChatGPT have entered the public mind since C.R. Rao was awarded the prize in 2021, I don't think it's impossible to imagine that the next award will be given to someone who has supported machine learning. My prediction for the 2025 prize is Vladimir Vapnik, one of the masterminds behind Vapnik-Chervonenkis theory, or VC theory. Machine learning and artificial intelligence today wouldn't be the same without VC theory. So that's my guess, but I can also see the committee choosing someone from causal inference or MCMC methods. If I'm wrong, but if I'm right, I totally called it. I'd love to know what your predictions are for the prize, so let me know in the comments who you think it might be. I like to think of statistics as the quiet hero of science. When it's done right, we expand our knowledge and create new technologies and medicines that help us out. But at the same time, we often focus on the achievement rather than the method that made it possible. And this is where the prize comes in, to honor those who have helped make these achievements possible. Even if the general public doesn't appreciate what statistics has done, a little recognition never hurt anyone. Thanks for watching the video. If you'd like to get more statistics content, then consider subscribing to the channel. You can also get notified right in your inbox if you subscribe to the channel Substack. That's it for this one. I'll see you next time. Peace.